In our third and final lecture on Chapter 5 material, I'd like to take a look at two more problems and also revisit Newton's third law to show an alternate way of writing it. Now, that said, I want you to think about two blocks that are connected by a string that hangs over a pulley. One block sits on a table and has a mass of 2.25 kilograms, and the other hangs over the side of the table and has a mass of 5.500 kilograms. I want to know what acceleration each of the blocks are going to experience. Now, so here's a table. Right here. I still have the bold on. And here's a pulley that we're going to hang our string over. So let me move this over here. Like that. And here are two masses. We'll put one right here. And then there's going to be one right here. So you have a string that goes from one mass to the other mass, and it goes over the pulley. So here it is, hitting the pulley here, and then it comes over the edge of the pulley and goes on that one right there. Now let's label these things. So this I'm going to call M1. This one I'll call M2. M1 here has a mass of 2.25 kilograms. M2 has a mass of 0.500 kilograms. Now, we're going to assume that the blocks start at rest. It really doesn't matter. We aren't talking about friction or anything like that in this particular problem. But what I'd like to point out here is the following. The blocks are connected. This system right here is an example of something called a composite object. So this one object, that is two masses connected by a string, are made up of other things, two masses and a string. So that said, let's write down what we've been given. We have two masses, M1 is equal to 2.25 kilograms, M2 is equal to 0.500 kilograms. Now, what's going to make these blocks move, or at least have their motion changed, is the acceleration due to gravity. So we know mass 2 has got mass. It's in the presence of the Earth, which means that there is a force due to gravity that mass 2 is going to experience this like this. Now we also know that this table represents a solid object that's a boundary. The block can't move beyond it. So it pushes into the table and the table pushes back. Why does it push into the table? Well, it too has a weight. So we'll call this Fg1. Now, both of their weights are obviously due to the acceleration due to gravity. Since this pushes into the table, there's a normal force, like this, which I'm going to call N1 just to associate it with the first mass. Now, there's a string present. Strings convey tension. They convey forces rather via tension. So we know as this mass pulls down, the string is going to become taut and there'll be an upwards tension like that. This tension, since in a string or a rope or a cable or something like that is the same at all points, when it connects to here, it's going to pull this way on this mass right here. Now, remember, tensions are the same at all points inside a cable, a string, or whatever. So the directions of these two tensions may be different. This one, for example, to the right and this one up. But in magnitude, they are the same. Now, since we have two objects here, the way to join them and make them act like one object is to draw two force diagrams. So over here, let's draw our force diagrams. That's for object 1. And this is for object 2. So, object 1, object 2. Here's object 1, mass 1. Here's mass 2 right there. For mass 1, right here, we have a tension to the right. We have a normal force that's up, and that is in response to gravity pulling down like that. Let me fix that right there. So, here's our normal force. Here's our tension. And here is our weight. Like that. For mass 2, we have the weight and we have the tension. Just like that. Now, so before I go any further, I'd like to point something out. These things are connected by a string. So let's pretend that I put my hand here and I pulled this thing down. Well, presuming that the string is not elastic, and we're making that assumption right now. This is a consistent assumption throughout the entire course. The strings do not act like rubber bands. There's no elasticity to them. They don't stretch, okay? So that said, if I pull down on this, we'll say, let's pretend I pull down at a rate of 1 meter per second. This should move to the right at 1 meter per second because it's connected. If I were to start from rest and accelerate this thing downwards, this should feel the same acceleration to the right. So the point that I'm trying to make here is that even though the accelerations for these objects are in different directions, the magnitudes of the accelerations are going to be the same. Okay, so that said, let me break up this problem. We're just going to draw a line right down the middle like this, like that, just to separate the two sides. Because what I want to do now is to look at the net force. We'll start with object number 1. So here, for object number 1, if I look at the external force here, okay, I have 3 forces. I have a normal force, I have a weight, and I have tension. Okay. Now, these most definitely are not going to add up to give you 0 because this thing is going to accelerate to the right as this falls. So they add up to give you m1 times a1. The forces here act on this mass to cause it to experience this acceleration. Now, don't forget the magnitudes are the same. We're going to come back to that here in a moment. Now, that said, the table again presents an unyielding object. The mass can't move past it. Okay, so what that means is here the normal force and the weight are going to cancel each other out. So if I were to look at what's going on in the y direction and look at what's going on in the x direction, here's what I see. In the y direction, I see a normal force that points in the positive y direction, but I also see a weight that points down. So it adds in as a negative. And those are going to balance each other out to give you 0. Now, in the x direction, though, if you look at the tension here, there's no force other than tension that lies in x, which means there's nothing to balance it out or take away from it or add to it. So what that means is that we have a positive tension, okay? And that tension is going to act on mass 1 to cause it to accelerate to the right. I'll put a 1 here just for consistency. Now, let's not forget again that the acceleration in magnitude is going to be the same in both cases. Now, so let's take a look at number 2 now. If you look at all of the forces that are acting on number 2, you have a tension and you have the force due to gravity. Okay, it's weight. Now, these again are most definitely not going to add out to give you 0 because number 2 is going to accelerate downwards. Number 1 is going to accelerate to the right. The tension is positive, but the weight is negative. Now, this difference is going to act on mass 2 to cause it to experience acceleration downwards. Okay? Now, there's nothing interesting going on here in x. Again, you look at x and y. Just in y. So this is just going on in y. In x, nothing. Okay? Now, but look at the direction of the acceleration. These guys are going to accelerate this way, and this one's going to accelerate this way. So, it's a vector, remember, and it's down. So writing it this way, this is the magnitude of the acceleration, and this is its direction, and this is the magnitude of the acceleration here. But remember, the magnitudes are the same. So what I'm going to do is to call AX1 and AY2, should be a 2 there for consistency, just A. I'm just going to call them A. All right? Now, so if you do that and you rewrite your equations here, the top equation says N1 minus, now what was the weight? M1 times G is equal to 0. This equation right here says T is equal to M1 times A. All I did was just change this to A since they're both the same magnitude. This one right here, when you rewrite it, says the tension minus M2 times G, so that's the other weight, is equal to minus M2 times A. Now, you can see the tension is what's conveying this force. So I'm going to take and plug this right here into this right here. And when I do that, and I want to continue writing it right over here under this, you get M1A minus M2G is equal to minus M2 times A. I'm going to move this to the left-hand side and this to the right-hand side. I'm going to group the masses together and pull the acceleration out. And what I end up with is M1 plus M2 times A is equal to M2 times G. Now, let's look at what this is telling us, right? So this really, remember, is the weight of object number 2. The force right here, its weight, is moving both masses. All right, it's moving both masses, not just M1, but also M2. This is your composite object right here, okay? So if you want the acceleration, all you have to do is to solve for it. It looks like this. Now, what was M2? M2 is 0.500 kilograms. And G is just the acceleration due to gravity. Then you divide by the sum of the masses. 2.25 kilograms plus 0.500 kilograms. Now, let's go ahead and do the math here. 0.5 times 9.8 divided by 2.25 plus 0.5. And I get 1.78 meters per second squared. Now, so what does this mean? Well, block 1 is going to accelerate this way at this acceleration right here. But block 2 is going to accelerate this way at this acceleration right here. Now, 3 sig figs, 3 sig figs, 3 sig figs. And this right here is our answer. Okay? Now, so it's one example. Let's do another. This is a little more complicated. So in this one, we have two blocks on an inclined plane. And M2 is hanging off. M1 is obviously headed up the incline. And what I want to know is what angle would you have to incline this thing to in order to have the forces balance each other out and for its motion basically to not occur. So we want the actions here to cancel each other out on this composite object. Okay. So what are we given? Oops. The mass on the right is 0.25 kilograms. The mass on the left is 0.75 kilograms. Okay. Now, so I propose that just like before, we play the same sort of game. We're going to rotate. You remember how this works. Let me sort of cut and paste this thing. So what we're going to do is to rotate this thing so that the plane acts like the x-axis. Okay. Now that's going to affect ML's weight direction, the direction of its force. We're going to have to look at that. But it's not going to really affect MR. Now, why would it not affect MR? Well, remember, ropes and cables and strings convey force. As this goes up and down, this is always pointing straight down to the ground. So, here's what we're going to do. We're going to redraw our picture and we're just going to look at the behavior of ML. Now, our x-axis is the inclined plane. The y-axis is normal to the plane. Normal means straight up at right angles from, remember? So this is going to be our y-axis, and this is going to be our x-axis. I'm going to place the center right here as being where our block is. Now, as drawn, we have a tension that goes this way. But when you look at, for example, here, when you look at this in the plane, our weight goes off this way. Okay, that was actually a pretty good straight line. I'm not going to use it though. It goes off like that. Now, once again, exactly the same arguments apply. This angle right here is theta. It's the same thing. Now here, we have our normal force that goes straight up like that. Okay, so this right here is going to be the free body diagram, or at least it's going to give us the free body diagram for the left object. This is ML. Okay, so to label these things, this is our normal force. This would be the tension. Remember, the tensions are the same. Okay, And this right here would be the force due to gravity on the left thing. All right. Now, so the right one, it's unchanged. So when we draw our free body diagrams, which I'll do over here, that's number 1. This right here is number 2. This will be the left side, and this will be the right side. For the left side, after we've rotated our coordinate system, we have the tension to the right, we have the weight going down that way, and then we have our normal force going up. Looks like that. Now, for this object right here on the right side, whoops, we have a tension going up and we have a weight going down, and that's it. Okay. Now, so, in all of these problems, or at least the ones we've been working recently, the big motivator here is the acceleration due to gravity, right? So, excuse me. So, just like before, I want to take a look. We'll separate things, and this time I'll separate it this way to be different. That. So, for this one right here, when I look at the external forces, all the forces that are acting on it, I see 3. I see a normal force, I see a tension, and I also see the force due to gravity. Right? Now, again, these are adding up to, in the situation that we want, give us 0. We want these forces to add out because what we want to do is to incline or decline this thing so that we can prevent the block on the right from pulling the block on the left. So we want the forces to balance each other out. I mean, technically it's still pulling it, but what we don't want is net acceleration. So we're looking for the situation specifically in which this acts on the left object to give you 0. Now, that means in the x direction, we're going to get 0, and also in the y direction, we're going to get 0. So what do we have going on in the x? Well, we have a tension that's very much positive, but then we have this force due to gravity here. It's its x part that's negative. Okay? Those are going to have to add out to give us 0. In the y direction, which is really not interesting to us right now, we have the normal force, which goes up, but then we have the force due to gravity that goes down. And those, again, are going to balance each other out to give us 0. Now, for the right object, when you take and you add up the forces, you have 2. You have a tension that goes up, and whoops, and you have the weight due to the right one. Having a day. There we go. That goes down. But these are also going to balance each other out because if this one isn't experiencing any change in motion, this one shouldn't be either. Okay? So here, in x, there's nothing interesting going on. But in the y direction, we have a positive tension and we have a negative weight. Okay? Now, so we have this x and this y part of this one. We're going to need to break that up into components. So let's go ahead and do that. I'll draw it like this. This is the weight. This would be the y part, and this would be the left part, or the x part. Here's our angle. Okay, so here, if you think of opposite, adjacent, and hypotenuse, FGLX, that one is opposite, so that's a sine. Okay. If you look at the y part, that's adjacent. That's cosine. All right. So those will go in here, and let's do that real quick. FGLX, that's FGL sine of theta. This one is really not useful to us. We're going to go ahead and do it anyway. That's going to equal to 0 as well. Now, so let's not forget what our weights are. FGL is the weight of the left side. FGR is the weight of the right side. Right? Okay, so let's take all of our equations and just sort of sum them up over here. From object on the left, we have T minus ML times G sine theta is equal to 0. That's this equation right here. This equation right here is N sub L minus MLG times cosine of theta. This equation right here, T minus MR times G is equal to 0. Now these two equations are what we want right here, because the link between the two objects is through the tension. This right here is just a statement of Newton's third law and normal forces. So if I were to solve this for T, and then plug it into that, I would have the following. Now the G's cancel. All right. And what we have here is that MR minus ML sine theta is equal to 0. If we solve for sine of theta by moving this to the side and then dividing both sides by ML, we get this. Now what we're going to do is to take the inverse sine of both sides. When you do that, you can get the angle. From that. So what's MR? Well, that was up here, 0.25 kilograms. ML is 0.75 kilograms. So 0.25 kilograms over 0.75 kilograms, like that. And when you plug that into your calculator, and make sure your calculator is in degree mode, you get an angle of 19.47 degrees. Now, keeping to 2 sig figs, this would be 19 degrees about. Okay, so what angle do you need to incline this thing to? About 19 degrees. At that point, this part, or this, hold on. At that point, this weight right here is being balanced out by the part of the weight that's down the incline right here. Okay? Alrighty. So, those are the only two problems that I really want to work. What I would like to do now is to revisit Newton's third law and remind you about it, basically. If object A exerts a force on object B, this is the force of A on B. B exerts the same force back on A. It's just opposite directions. Now, so that said, if you look at the equation for force in general, it looks like this. But this isn't really a very good way of writing it. Because what if your mass can change? Now, what we do in that case is the following. I'm going to take and write this acceleration as the change in velocity over time, the derivative, and then noting the fact that mass, at least in the cases that we've been dealing with, is constant. I'm going to pull this into this. Now, this mv thing actually has a technical name. It's called momentum. We're going to be talking about it after we talk a lot about energy and stuff. That said, it's denoted as a p, it's a vector, and it's mass times velocity. Okay, so another way of writing Newton's second law, and also the third law, is by looking at how the momentum changes with respect to time. And this right here is actually closer to what Isaac Newton had written down. Okay, this is closer to what he wrote down. He really didn't write down the whole F is equal to ma thing per se. This right here is a much better descriptor because now you can talk about situations in which the mass is not constant. Examples of which might be a rocket. For example, rockets, when they lift off the ground, that's a very terrible looking body of a rocket. So I'll use this, like a Bugs Bunny rocket type thing like that. Let me see here. Clip the bottom off here just a little bit, like that. And then I'm going to put a bell here, like that. And I don't know, some Bugs Bunny wings, like that. Why not like a little bubble there? Looks good. Now on the inside of your rocket, you have fuel, like this. I'm just going to sort of draw it a little bit like that. So this is your fuel tank, right? Sits in here. And what happens is through combustion, fuel is forced out the bottom, basically. All right. Now, as fuel is forced out of the bottom, then the mass of your rocket, which is really the mass of the rocket itself plus the mass of the fuel, this decreases. And without doing this, you can't really talk about what's going on here. Now, we're going to come back to momentum later on, like I said. We need to further develop understanding of forces and stuff, which we'll be doing in Chapter 6. So that said, I think it's a good place to stop, and that's it.